Okay, so our next speaker is Lakshmi Subramanian. Lakshmi is an associate professor at the Quran Institute of Mathematical Sciences at NYU, which I guess means he gets to live in Manhattan, which is really cool. His research interests are network systems, computing for development, and big data analytics. Lakshmi also co-leads the Center for Technology and Economic Development and is a member of the NYU Systems Group. And finally, he's PhD number 31. So.
I thought I was PhD number 36, but anyway.
Well, that's not what his list says. So.
Is there a?
Yeah.
Okay. So this is a talk that I've never given before, and I thought Randy at 60 being a special event should be something where we should talk about something. So I'm actually talking about my startup, Entropy, which actually jointly started with Eric Brewer and my PhD student, Ashlesh, who's the CTO, and Vidyut. And before I start on this, being here at Berkeley, there were certain amazing things that I learned being advised by three elders, Randy, Scott Schenker, and Jon Stoica. And one of the biggest things I learned was to be a little bit fearless. And in the sense that right after finishing my PhD when I joined NYU, essentially I completely shifted style of research to developing countries. So most of my work is on computing for development. And people at that time thought, oh, this is going to be tenure risky and all that stuff. And it's great to finally say, last year 4 universities, Cornell, Georgia Tech, Michigan, and Washington, made faculty offers in the space. We were at CRA giving talks to deans on why they should be hiring in the space. So it's finally good that, and I was the first guy to get tenure in that space, so it was kind of crazy. But we had to start our own conferences, we had to start our own journals, and it was been a fun experience. And this startup actually it came out of that experience. And when you work on developing countries, you have to go beyond your comfort zone. You're not a networking person anymore. You're not a systems person anymore. You're, by some margin, a computer scientist. And you sometimes have to learn the problem. So we go out in the boondocks in India and Africa to actually deploy systems. And you have to understand how healthcare works, how education works, to actually solve some of these problems. And fingers crossed, so far we've had a few successful deployments at very large scales in many of these countries. And a few startups have come out of many of these efforts, thanks to a lot of help from Eric Brewer. I should also thank Gaetano Borriolo in remembrance. I was in a very difficult spot in December when I had lunch with him, and he was like, man, I have 1 more month to go. And it was very difficult. I almost cried. And he's been sort of like a godfather in the whole developing country space, and he has single-handedly championed a lot of some of the greatest people who have come to work in the space. So in that regard, let me start on Entropy. And Entropy has taken me into a world of computer vision, machine learning, optics, microscopy. It's been fun stuff. And it really started with something called as the Telgi scam in India. So there's a stamp paper scam, which is about $6 to $10 billion. And people were printing fake stamp paper for about 20 years. So the property that you have, you own this house, somebody else can claim, I also own this house, and can take you to a court of law. Right? So it was a massive scam. And so essentially, we came up with a solution where we can prove to you that every product line and every physical product is unique. So all of you are sitting in chairs, and I can actually prove to you that each chair is different without changing the chair. And the key idea is we built a microscope which can take sort of microscopic textures, and I can understand variations in microscopy of textures to uniquely identify any physical object. And the second aspect of it is I can also learn similarities in the production of these chairs to tell you that the product line has some uniqueness. Okay? Now, why in the world would I want to do this? And the key is counterfeit goods. Counterfeit goods is a $1.7 trillion problem. 7% of world trade is counterfeit. We might be living in a nice sphere where we might not be exposed, but when you actually go into the boondocks of what's actually happening with respect to supply chain management, 7%, 25% of Louis Vuitton bags to 50% sold on eBay is fake. Okay? eBay had to pay $63 million to Louis Vuitton. And there are lots of fake watches. There are more fake watches than real watches. And there are massive losses in each of these markets. Okay? What do we want to do? We want to build a startup. Sorry, I missed the joke. What is the joke? Okay. And fantastic.
You really haven't seen your slides.
Yeah, I haven't seen my slides. So we want to build a layer which enables trustworthy commerce. I want to enable trust in every transaction, every physical good transaction. And we want to solve the counterfeit goods problem. So we want to sort of become the standard where we sit in the middle to authenticate any physical good. And it has value propositions for brands, retail, resellers, distributors, pawn stores, marketplaces, consumers. This is a very business slide, so I'm not going to take you through the details of this. Now, let me show you a more fun video. How do I play a video? So there's no audio coming here, but the video speaks 1,000 words. So what you see here is we microscopically take a fingerprint, then it automatically connects to your mobile phone. You just upload a texture, we just choose the brand, and you can say it's authentic. And you can test it on any part of the bag. And essentially, just using one or two images, we can tell you whether it's authentic or fake. So you just give me a bag, I just take 2 pictures, and I can tell you whether it's authentic or fake.
You have fast houses?
We have, I'll get into that in a few minutes, right? So what's actually happening? We've built an authentication ecosystem, right? So we have a microscope which connects to a mobile phone, right? And we have hired scanners who actually work out of many of these warehouses, right? And you give me one handbag, I essentially take about 600 to 1,000 pictures of that handbag at a microscopic level, right? I'll get into the microscope design in a little bit. And essentially, I've learned all the patterns of what a Louis Vuitton bag actually is, right? So even if you give me a super fake where the canvas is original but the printing process is different, I can tell you, okay? And we've done this at scale, and now we've just released our beta, and things are going really well. So here is an authentic and a fake bag, right? To the human eye, that's how they look. When you look at it microscopically, they look very different. The patterns are very different. So they sort of look similar at the human eye, but the printing patterns, so if you look at a monogram, the dot pattern of the printing and the spacing between the dot patterns, the randomness around the dot patterns are all very different. So I can learn the genome of a product line, and I can learn the genome of a bag. To learn the genome of a bag, I need to fingerprint at the same spot. To learn the genome of a product line, you can keep it anywhere in the bag. So that's the beauty, okay? So how does this work? So it's a massive deep learning system, okay? So we had to build like a very complex 24-layer neural net. Some of Google's neural nets are 21 layers, so we have 3 more layers. And so what you see here is an example neural net. I'm not putting our exact neural net there, right? And we have scanners, we have struck deals with partners who give us access to handbags. Believe it or not, one of the hardest things was I realized I could not be the front person doing this because, going to a lady and asking for her handbag was one of the toughest things. So getting inventory to scan was a very difficult thing. And finally, thanks to an amazing CEO and an amazing VP of sales and marketing, we have been able to essentially strike deals with Poshmark, RealReal, Threadflip, or Lynda Stuff. I don't know how many of you have heard, but Lynda Stuff is largest eBay reseller. And we work with a very interesting person called Max Pawn. Okay? He's the head of the National Pawn Association. Now, there are 14,000 pawn stores in the US, right? And in Las Vegas, people have stopped pawning jewelry and are now pawning handbags. This guy opens up his warehouse and he has 5,000 handbags, each worth at least $3,000. So rich guys come in, pawn their handbags, and take a loan, right? And he doesn't know whether it's authentic or not. So we have like massive demand from the pawn industry, right? And we are presenting at a pawn expo in Las Vegas today. So it's a very ghetto business, right? Like you're looking at the boondocks to actually build up. And so we have scanned a lot of inventory right now. And we've scanned about 1,500 handbags. And I know very little about handbags, but lately I've learned a lot about handbags. And what essentially happens is, given an image of any particular spot, we train a massive neural net, and we're able to classify with very, very high accuracy. So overall, for a single image, we're able to achieve an accuracy of 99.4%. Okay? For the outside texture specifically. By that I mean a real is classified as a real with 99.4% accuracy, and a fake is classified as fake with roughly around 99+% accuracy. And we've been doing this for Louis Vuitton Monogram, Louis Vuitton Damier Bean, Damier Azure. In case you don't know any of these, you're not lost. But lately we've been doing it for Tiffany's bracelets, Rolex watches, and we're expanding. I mean, some of the crazy people who want to work with us are like people who make Air Jordan shoes, and we've had interest from NBA to fingerprint NBA merchandise. So lots of crazy. Now, at a one of the crazy things that made this happen was we had to make our own microscope. So we zoom at a 300x magnification. Okay? Now, 300x magnification with a 5 micron or lesser granularity. And if you want, so we're able to do that with a capture of 1 centimeter by 1 centimeter. A traditional microscope at 300x gives you 2 millimeters by 2 millimeters. So essentially, you need a much larger coverage. Now, all the top lens manufacturers in the US turned us down to manufacture the specific lens set. So this has a very complex lens element of 6 lenses. And wider the angle, the smaller the lens. And you have to be very careful about curvature of the lens and thickness and errors. So we had to go through 2-3 trials with a few vendors to actually get the lens design correct. Okay? So that was one part of it. Then you need to put a diffuser, and you need to put like a polarizer in front to make sure that the light pattern is uniform, so that you don't have any blur effects. And then on top of this, it has a full-fledged embedded system. So it runs an umbrella chipset split across 5 boards, because you want this to be compact. This, I mean, if it's a lady's device, it has to fit in a handbag, right? So it's fairly within a handheld, and it's essentially a very similar design as what goes into a GoPro with a Wi-Fi board on it, and that does real-time streaming of the. So it's a very complex engineering to actually get it right, and we're going through like version 4 of hardware right now. And the second aspect of this technology, using the same hardware, I can uniquely fingerprint each bag. So it's almost putting like a tag without putting a tag. Okay? So what is shown here is microscopic texture speckles of metal, canvas, paper, glass, plastic, and so on, right? Where essentially you give me different laptops. What happened?
I have a question.
Yes.
So in the example you showed, the LV bags are more synthetic made, so that you can actually look at the texture. How about the real leather? Each pig is each color is different. They have a different texture. How would they actually?
So we can do. Let me just complete this part, and then let me answer that question. But at a high level, we can do both similarity matching and dissimilarity matching. So I have to answer your question on both sides. right? In terms of similarity matching, if you have leather texture finished leather, right? I can apply it for the finished leather. If you have unfinished leather, similarities are going to be much smaller. So when I look at it at a Louis Vuitton product level, it's actually finished leather. When you look at it just as scarf skin coming in, it's actually unfinished leather, and the similarities are much lesser. Okay? So going back to texture speckles, what is actually happening here is we can look at speckle patterns that arise based on how light reflects off a rough surface, right? And we can essentially extract a unique texture pattern for any physical object as long as you place it on the same. Now, one of the beautiful things about a 1 centimeter by 1 centimeter microscope is I can place it at the same spot. Human error for 2 millimeters is very hard, but human error for 1 centimeter is actually quite good. So even with partial overlap, we can create a match. And these are more texture speckle patterns for other things. Now, to answer partly your question about speckle matching of plain leather. So I actually went to leather factories and as I got raw samples of, I have a huge stack of random leather samples of every type of skin, but that's a different story. So this is like 2 random pieces of the same piece. So we created a manual database, right, of just pure leather patterns, right, just random leather patterns. And after you scan each one of them at a particular corner, you just take a random piece and say whether you can match, right? And we are able to show that you give me 10,000 pieces, I can uniquely identify each piece apart. And the key idea here is we identify sort of local descriptor features using computer vision and then do local descriptor matching. Okay? Now, the local descriptor matching may not be perfect. So if you look at currency bills, for example, right, the local descriptors, which are literally curvatures. I have 5 more minutes. I'll be done a bit before that. So local descriptors almost match, but they don't always match. So you can see some lines that are going off track, right? So you have to be sort of error tolerant a little bit in doing the matching. And yet, if you get a geometry of sufficient points where they align, you can actually say it's the same currency piece. But this is an example where it's all over the place, where for two checks, okay? And we specifically looked at 2 checkpoints where the writing was the same, and still you can see the difference, right? Now, this is a very interesting slide. We've actually tested this on wear and tear, aging, soaking it in water, soaking it in oil, crumpling the piece of paper, right, across materials. And essentially the key point is, across all these, you can choose a threshold that you can handle all these things to quite a bit of a degree. If you take a knife and really chop that region, right, you can kill the fingerprint. But yeah, you need to put some effort. Okay. So the other crazy thing was, when you take these types of images, right, how do you define entropy? How do you define how much is random, right? This is a very hard question in information theory, right? Because you do not know the probability distribution over the entire space, right? So what we've been able to do is we've been able to use SIFT feature vectors, right, where over a 16 by 16 grid, so sort of define descriptors around 16 by 16 grids, pixel grids, and take the 4 corners, right? And you can run mutual information tests across correlation, cross-correlation across these points, and you can see how independent these points are, right? And then you can define an entropy just around these 4 points by converting them to a vector space. And essentially the key thing is, we've been able to extract roughly 30 bits of entropy as a lower bound per key point. And we have so if you are extracting 50 key points to match, you're essentially getting 1,500 bits of entropy, which means you can get 2,500, 2 power 1,500 unique physical objects that are covered. So we have signed up a lot of partners: Linda Stuff, Poshmark, Maxpawn, Threadflip. We've just released a beta, and we're working, testing it for Louis Vuitton. We're just releasing the product. Taking a step back, one of the things that happened through my Berkeley times till now is I've been looking at a lot of different projects with the basic theme of authenticity of an identity. And when I look back, as part of my PhD, I looked at it for internet routing, then I did for online content voting, social network identities, DNS names, paper documents, crowdsourced content. We are now looking at mobile identities and so on. But that's sort of like a theme that has really come across. And that, when Elon and others said, you have to actually finish your PhD, there are certain things that remain as a thread. And that's something you actually come back to a lot. And I was also flipping through my thesis. And there is one seminal contribution in my thesis that I would love all of you guys to read at one particular point, which is the acknowledgement section. And I actually wrote a poem for Randy Scott and Jon called An Ode to the Three Elders. It was a very carefully thought poem written at that time. And I don't want to go through it in great detail, but a key sentence here is the impatience in my mind, the very thought of gold should go, right? And when you go through the whole PhD, right, you see an astounding heap of gold lay in front of you, right? Am I at El Dorado? And you think you're kind of done. And momentarily you feel blinded by the glitter of gold by daylight, but thinking back, you left without a single piece into the cold, dark, stormy night. So what you actually take away is not just a heap of gold, but the lessons that you have learned going through the PhD, and that becomes way more important than the heap of gold that you might see. So with that, let me stop here and take questions. Thank you. Yeah.
So there was a paper published at the UBCOM conference a month or two ago from the University of Washington. Gaetano actually was a co-author and some folks at Microsoft Research on making inexpensive hyperspectral cameras. Would that kind of camera be good for this type of problem? Because they tend to show you more of the underlying structure of the item.
Definitely yes. Definitely yes, at a short level. And we have also thought through, like, how do you use, so I've spent a lot of time reading Renning's works on light angle of arrival, and there have been also many SIGGRAPH papers on these types of designs. And wide angle microscopy is right now something that is getting pretty hot. And yes, so there's also a company called Light.co, which is releasing their product on essentially using several cameras and essentially using a huge number of features to virtually extract sort of like a 52 megapixel photo, but each camera is barely recognizing at 5 megapixels. So yeah, many of these things would definitely help. And for us, the main thing was we were trying to use standard microscopes, and we were trying to do it. And we reached a point of failure where we had to realize, holy shit, we have to design our own microscope. And the way we had designed it was like trial and error. We learned optics and figured out a wide angle microscope design. But yeah, certainly we are not like super optics experts too. So yeah, we have been reading a lot of these papers and trying to adapt as much as possible. Yes.
So I had the next question. So you talked a lot at the beginning about your work in developing regions, and this doesn't, I mean, the stamp paper part is definitely relevant, but the rest of it doesn't seem to be that directly relevant. One area that I have seen in developing regions where authenticity is really important is that of medicines.
Yeah.
Because there's a lot of sort of fake medicines floating around.
Fair.
I'm not sure, can this actually work for that?
So here is a larger piece of thinking for anybody doing startups, right? We have actually gone through very tough times to get to where we are right now. And we spent a lot of time on paper, on educational documents, diplomas, essentially realized we need government contracts or to break into systems which are very hard to break into. So we were even looking at countries to print their entire new currency supply chain. Didn't work out. We spent a lot of time in art. I've spent time with billionaires fingerprinting artworks until I realized, there are people in the system who own fake and real of the same piece. I saw the Andy Warhol Foundation shut down in front of my eyes. And we dealt with people who were marginally, suspect. So for lack of other choice of words. So finally, we kind of struck gold in handbags, right? So it's been kind of an evolution for us to essentially hit a market where it has direct applicability. People immediately want to use it. We've done practice things in like 4 art exhibitions, Met, MoMA, Fales Museum. We've done like several things. And in art, we actually failed. And then this was a pivot. Because I was under the hood of NYU, I could experiment and kind of wiggle my way around. But otherwise, this the company would have already shut down by now if we had not done that.
Last question. Yeah, so you mentioned that you're using a 24-layer deep neural net.
Yeah.
So to train something like that, you would need an enormous amount of data.
Yes.
So can you tell us how you actually got the data? Like, I mean,
yeah.
You need labeled data that tells you this is genuine and that's not genuine. So how
Yes.
do you actually get that?
So we actually work with human authenticators. So what we do is we have scanned 1,500 bags, let's say, Louis Vuitton bags, and we take 600 to 1,000 images per bag. So that's about 1.5 million microscopic images. Now, when you look at it, then you can use a whole bunch of computer vision algorithms to generate a lot of similar looking data by stitching and so on. So we can multiply that number by a factor of 30, right? And you can also sub-slice an image because these are huge images. You can take the same image to represent smaller regions, bigger regions, and so on. So we essentially deal with a training data set of about 30 million images. And then we train a whole massive net. Now, when humans stamp it, human authenticators stamp it, there is error, right? So we first do clustering, then we do several 90-10-fold testing. And there are certain cases which don't match. So we actually have to manually take them out of the data set. So there's a lot of process that goes into curating the database to actually do. And that would be a huge barrier to entry for somebody coming in, because getting access to 2,000 handbags is not that easy. And because each one is $5,000, so that's $10 million of inventory. So.
All right. Well, with that, let's thank Lakshmi once more for a very entertaining talk.